Welcome back to Science Sleep Stories. Tonight we're embarking on a journey through time unlike any other. We're going to explore the deep future of our home planet, tracing Earth's story forward through billions of years, watching as familiar landscapes transform, as oceans vanish, as the very air we breathe changes its composition, and ultimately, as our world meets its fate beneath an expanding, dying sun. The earth beneath your feet feels permanent, eternal even. The mountains have stood for millions of years. The oceans have lapped at continental shores since before the first fish crawled onto land. The sun rises each morning with such dependable regularity that we build our entire civilization around its predictable rhythm. Yet everything in the cosmos, from the smallest atom to the largest galaxy, exists within the framework of time, and time transforms everything it touches. Our planet is 4.54 billion years old, born in the fiery crucible of the early solar system when dust and gas swirled around our infant sun, gradually coalescing into the rocky worlds we call the inner planets. For most of its existence, Earth has been a dynamic, living world, constantly reshaping itself through the movement of tectonic plates, the cycling of water between ocean and atmosphere, and the steady chemical dance between life and the environment that sustains it. But this age, this comfortable era of stability and abundance, represents just one chapter in Earth's much longer story. The future stretches out before us, vast and largely empty, measured not in centuries or even millennia, but in eons so long that human comprehension struggles to grasp their true scale. What awaits our world in that distant tomorrow? When will the conditions that make Earth habitable finally fail? How will our planet spend its final days? These aren't questions of idle speculation. Scientists can predict Earth's future with remarkable accuracy, because the forces that will shape it are the same fundamental laws of physics that govern everything in the universe. The sun will continue to age according to the well-understood principles of stellar evolution. Earth's interior will continue to cool as heat radiates away into space. The carbon cycle will respond to changes in solar output following predictable chemical pathways. The laws of thermodynamics ensure that all ordered systems must eventually decay. So tonight, we'll trace that timeline forward. We'll start in the relatively near future, when Earth still resembles the world we know, and then venture deeper into time, watching as our planet transforms in ways both gradual and catastrophic. We'll witness the slow death of photosynthesis, the boiling of the oceans, the cessation of plate tectonics, and finally the moment when Earth either burns in the expanding atmosphere of a red giant star or becomes a scorched, lifeless rock orbiting a cooling white dwarf. The story we're about to tell spans more than 7 billion years, from now until the moment our sun exhausts the last of its nuclear fuel. Along the way, we'll encounter timescales that dwarf human history, changes that make our current climate concerns seem like fleeting weather patterns, and a vision of Earth's ultimate fate that is both humbling and strangely beautiful in its cosmic inevitability. This journey begins now, in our present moment, and extends forward into a future where no human will ever set foot on this transformed world, where the very concept of Earth, as we understand it, will have long since ceased to have meaning. Yet understanding this future helps us appreciate the precious, temporary nature of our current home, this brief window of cosmic time when Earth happens to be the perfect place for complex life to flourish. So settle in. Let the regular rhythm of your breathing anchor you to this present moment, even as we travel forward through the ages. The journey ahead is long, the change is profound, but the story of Earth's future is one written in the language of physics and chemistry, as inevitable as the sunrise and as certain as the turning of galaxies. Let's begin. In the immediate future, measured in mere millions of years rather than billions, Earth will remain recognizably itself. The continents will continue their slow waltz across the surface, driven by the churning convection currents in the mantle below. Mountains will rise and erode, oceans will expand and contract, The climate will shift and change in response to variations in Earth's orbit, the arrangement of land masses, and the slow increase in the Sun's luminosity. But even in this relatively near future, profound changes are already in motion, set in motion by forces far beyond human control or influence. The Sun, that reliable golden disk that has illuminated Earth for more than 4 billion years, is not a static object. Like all stars of its size and mass, our Sun is slowly but steadily growing brighter. Every 100 million years, the Sun increases its luminosity by approximately 1%. This sounds like a small change, barely perceptible on human timescales, but over hundreds of millions of years, this gradual brightening has enormous consequences for Earth's climate and habitability. Since the Sun first ignited nuclear fusion in its core 4.6 billion years ago, it has already increased its brightness by roughly 30%. The young Earth receives significantly less solar energy than the planet does today. This creates an interesting puzzle for geologists and climatologists, because we know from the rock record that Earth had liquid water on its surface even in those early days. How could a dimmer sun have kept the oceans from freezing? The answer lies in Earth's atmosphere. The early atmosphere contained much higher concentrations of greenhouse gases, particularly carbon dioxide and methane, which trapped enough heat to compensate for the fainter sun. Over billions of years as the sun brightened, these greenhouse gas concentrations decreased, maintaining Earth within a habitable temperature range. This is the planet's natural thermostat, the carbonate-silicate cycle, constantly adjusting the atmospheric composition to keep temperatures stable. But this balancing act cannot continue forever. The sun will keep getting brighter, and there are limits to how much the Earth system can compensate. Looking ahead just 100 million years from now, the sun will be about 1% brighter than today. This may sound insignificant, but climate models suggest this additional energy will begin to stress Earth's natural regulatory systems. The enhanced solar radiation will accelerate the weathering of the rocks, a process that removes carbon dioxide from the atmosphere. As CO2 levels drop, the greenhouse effect weakens, which ordinarily would cool the planet. But the sun's increased brightness more than compensates for this cooling effect, slowly driving global temperatures upward. 500 million years into the future, the geological map of Earth will look dramatically different from today. The continents, which currently drift at rates of a few centimetres per year, will have travelled thousands of kilometres. Some geologists predict that a new supercontinent will form, bringing together many of Earth's current land masses into a single enormous continent surrounded by a vast global ocean. This configuration would have profound effects on ocean circulation, weather patterns, and global climate. Supercontinents create their own unique climatic conditions. The interior of a massive landmass, far from the moderating influence of the ocean, tends to become extremely hot and dry. Monsoon systems form around the edges, but the heart of the continent becomes a baking desert. At the same time, ocean currents change their patterns when continents merge, potentially disrupting the transport of heat from equator to poles. During this era, life will continue to thrive and evolve, but the subtle changes in solar output will begin to affect the carbon cycle in increasingly noticeable ways. The weathering of silicate rocks consumes atmospheric carbon dioxide. Ordinarily, volcanic activity replenishes this CO2, maintaining a balance. But as the sun grows brighter and surface temperatures rise, the weathering process accelerates while volcanic CO2 emissions remain relatively constant, creating a slow but steady decline in atmospheric carbon dioxide levels. This decline has little immediate effect on Earth's climate because the sun is providing more energy anyway, but it sets the stage for the crisis that will unfold in the next phase of Earth's story. Plants require CO2 for photosynthesis. As atmospheric concentrations drop, photosynthesis becomes less efficient. Eventually, CO2 levels will fall low enough that certain types of plants can no longer survive. Roughly 600 million years from now, atmospheric CO2, Concentrations will have fallen to a critical threshold. Plants that use what's called C3 photosynthesis, which includes most trees and many food crops, require CO2 concentrations above approximately 50 parts per million to function. When levels drop below this point, these plants will begin to die off, fundamentally altering Earth's ecosystems and setting in motion the long, slow decline toward a planet that can no longer support complex life. But before we reach that crisis point, Earth will experience other significant changes. The Moon, which currently orbits about 384,000 kilometers from Earth, is slowly moving away from our planet. This happens because of tidal interactions between Earth and Moon. The Moon's gravity creates bulges in Earth's oceans, and because Earth rotates faster than the Moon orbits, these bulges are dragged ahead of the Moon. The gravitational pull of these bulges tugs on the Moon, gradually accelerating it in its orbit and causing it to spiral outward. As the Moon recedes, Earth's rotation slows. Currently, Earth's day is lengthening by about 2 milliseconds per century, an imperceptibly small amount on human timescales but significant over geological time. In a few 100 million years, the Moon will be noticeably farther away, and Earth's days will be measurably longer. This has implications for climate, because the planet's rotation rate affects wind patterns, ocean currents, and the Coriolis effect that shapes weather systems. The Moon also plays a crucial stabilizing role in Earth's axial tilt. Without the Moon's gravitational influence, Earth's rotation axis would wobble chaotically over timescales of millions of years, potentially swinging between nearly upright and tilted as much as 85 degrees. Such dramatic variations in axial tilt would create extreme climate fluctuations, with the poles alternately pointing directly at the Sun and then away from it. The Moon's presence keeps Earth's tilt relatively stable, preventing these wild gyrations. However, as the Moon moves farther from Earth, this stabilizing influence will gradually weaken. Models suggest that somewhere between 1.5 and 4.5 billion years from now, the Moon will have receded far enough that its stabilizing effect diminishes significantly. Earth's axial tilt could then begin to vary more dramatically, potentially triggering severe climate instability. At its extreme, this could render large portions of the planet temporarily uninhabitable, as the poles alternately receive months or years of continuous sunlight, followed by similar periods of darkness. Meanwhile, Earth's interior continues its slow, inexorable cooling. When our planet formed, it was entirely molten, a sphere of liquid rock gradually solidifying from the outside in. The heat from that formation, combined with radioactive decay of elements like uranium, thorium, and potassium in the crust and mantle, keeps Earth's interior hot enough to maintain the liquid outer core and the slow convection in the mantle that drives plate tectonics. But this heat is gradually radiating away into space. The core is cooling, the mantle is cooling, and eventually, these processes that make Earth geologically active will slow and stop. The exact timing remains uncertain because we don't know precisely how much radioactive material exists in Earth's interior, or exactly how efficiently heat escapes through the crust. Some estimates suggest plate tectonics could cease in as little as 500 million years if the mantle cools enough. Other models suggest the process could continue for another billion years or more. When plate tectonics does eventually stop, Earth will undergo a fundamental transformation. The constant recycling of crustal material will end. Mountain building will cease. The carbon cycle, which depends on plate tectonics to bury carbon in subduction zones and release it through volcanism, will be disrupted. Without this recycling, carbon dioxide levels in the atmosphere will change in unpredictable ways, potentially accelerating either warming or cooling, depending on whether volcanic outgassing or weathering and burial dominates in those final years of tectonic activity. The cessation of plate tectonics also has implications for Earth's magnetic field. The field is generated by convection currents in the liquid outer core, driven by heat escaping from the solid inner core. As the core cools, these convection currents weaken, and the magnetic field declines in strength. Eventually, perhaps 2 to 3 billion years from now, the outer core may solidify entirely, shutting off the magnetic field generator. A planet without a magnetic field is vulnerable in ways that go beyond the loss of auroras and compass navigation. The magnetic field deflects the solar wind, the stream of charged particles constantly flowing out from the sun. Without this protection, the solar wind directly strikes the upper atmosphere, gradually stripping away gases molecule by molecule. This process has already transformed Mars, which lost its magnetic field billions of years ago, from a world with a thick atmosphere and liquid water on its surface to the cold, dry desert we see today. For Earth, the loss of the magnetic field would accelerate the escape of atmospheric gases to space, compounding the other changes already in progress. Lighter gases like hydrogen and helium would escape first, but over millions of years, even heavier molecules would gradually be lost. The atmosphere would thin, the ozone layer would deteriorate, and harmful ultraviolet radiation from the sun would increasingly reach the surface. But all of these changes, dramatic as they are on geological timescales, pale in comparison to the crisis that will unfold as we move deeper into Earth's future. The real threat to life on Earth doesn't come from wandering asteroids, supervolcanic eruptions, or any internal geological process. It comes from the sun itself, our life-giving star, which even now is slowly but inevitably making Earth less and less habitable with each passing million years. As we move forward in time, the subtle changes we've discussed begin to accumulate and accelerate. The brightening sun, the declining CO2, the cooling interior, the receding moon, the weakening magnetic field, all of these processes are building toward a series of cascading crises that will, one by one, strip away the conditions that make Earth a haven for life. The first of these crises, the one that will mark the beginning of the end for complex life on our planet, is already approaching. In the cosmic calendar, it's just around the corner, a mere 500 million years away, and when it arrives, it will transform Earth in ways more profound than anything our planet has experienced in its entire 4.5 billion year history. Imagine standing in a forest 600 million years from now. The trees look different perhaps, but forests still exist. The sun, slightly brighter than the one we know, filters through leaves that photosynthesize much as they do today. Animals move through the undergrowth. Life continues, seemingly as robust and diverse as ever. But beneath this veneer of normalcy, a crisis is unfolding, one that will spell doom for nearly every living thing on the planet. The crisis is simple, almost mundane in its mechanism, yet absolutely catastrophic in its consequences. Earth is running out of carbon dioxide. For the past several billion years, atmospheric CO2 concentrations have been declining as the carbonate-silicate cycle responds to the sun's increasing brightness. Higher temperatures accelerate rock weathering, which consumes CO2. The weathered minerals wash into the oceans, where they combine with dissolved carbon dioxide to form carbonates that settle on the seafloor. Eventually, these carbonates are carried into the mantle at subduction zones and released back into the atmosphere through volcanic eruptions, completing the cycle. This process has kept Earth's climate remarkably stable, despite the sun's steady brightening. As solar output increased, CO2 levels dropped, preventing runaway heating. The system worked beautifully for billions of years, maintaining temperatures within a range suitable for liquid water and life. But the system has limits, and around 600 million years from now, Earth will begin to approach those limits. CO3 photosynthesis, the pathway used by most plants including almost all trees and many crop species, requires atmospheric CO2 concentrations above approximately 50 parts per million. Below this threshold, the rate of photosynthesis drops so low that plants cannot grow fast enough to survive. When atmospheric CO2 falls to this critical level, C3 plants will begin to die off. Some plants use a different photosynthetic pathway called C4 photosynthesis, which is more efficient at extracting CO2 from the air. These plants, which include corn, sugarcane, and many tropical grasses, can survive at lower CO2 concentrations, perhaps as low as 10 parts per million. But even C4 plants have limits, and as CO2 continues to decline, they too will eventually succumb. The death of plants has cascading effects throughout the ecosystem. Herbivores lose their food source, predators lose prey, decomposers lose organic matter to break down. The entire food web unravels from the bottom up. Animals might persist for a time, feeding on the last remaining vegetation and then on each other, but without primary producers continuously converting sunlight into chemical energy, animal life cannot persist. Meanwhile, a more subtle but equally devastating change is underway. Plants don't just provide food for animals, they also produce oxygen as a byproduct of photosynthesis. Every breath you take contains oxygen that was released by a plant somewhere on Earth. The atmosphere's 21% oxygen concentration is not a natural state for a rocky planet. It's the result of billions of years of photosynthesis, with plants and photosynthetic bacteria continuously pumping oxygen into the air. When photosynthesis declines, so does oxygen production. And unlike the gradual decline in CO2 that took hundreds of millions of years, the collapse of atmospheric oxygen will happen with startling speed. Researchers Kazumi Ozaki and Christopher Reinhard ran sophisticated computer models simulating Earth's future atmosphere, accounting for the declining CO2, the brightening sun, and the complex feedbacks between the geosphere and biosphere. They ran the simulation more than 400,000 times, varying parameters within their uncertainty ranges to build a statistical picture of what might happen. The results were sobering. Around 1 billion years from now, give or take a few hundred million years, Earth's atmospheric oxygen will begin a catastrophic decline. The process, once started, will be swift. Within perhaps 10,000 years, a geological eye blink, oxygen levels will plummet from the current 21% down to levels not seen since the Proterozoic eon, more than 2 billion years ago. Some models suggest oxygen could drop to less than 1/1,000,000th of current levels, effectively returning Earth to an anaerobic atmosphere. This isn't a gradual change that organisms might adapt to over millions of years. It's a crash, happening faster than evolution can respond. Complex animals, which evolved in an oxygen-rich world, and whose metabolisms depend on abundant oxygen for energy production, will go extinct. Insects, with their oxygen-dependent respiratory systems, will die. Fish will suffocate in oxygen-depleted oceans. Birds will fall from the sky. Mammals, if any still exist by then, will gasp their last breaths. Only certain microorganisms will survive this apocalypse. Anaerobic bacteria and archaea, organisms that don't require oxygen and, indeed, often find it toxic, will inherit the Earth. These microbes thrived during Earth's first 2 billion years, before the Great Oxidation event transformed the atmosphere. Now they'll return to prominence, but in a world very different from the one their ancestors knew. The loss of oxygen has other consequences beyond the direct effect on aerobic life. The ozone layer, which shields Earth's surface from harmful ultraviolet radiation, forms when oxygen molecules in the upper atmosphere are broken apart by UV light and recombine as ozone. Without oxygen, there can be no ozone layer. UV radiation, already more intense from the brighter sun, will rain down on the surface unimpeded, further damaging any surviving life and preventing the emergence of new complex organisms. The planet's chemistry will shift in fundamental ways. With less oxygen to react with, methane, hydrogen, and other reducing gases will accumulate in the atmosphere. The air will become thick with methane, a powerful greenhouse gas that will trap even more heat. Surface temperatures, already elevated by the brightening sun, will climb still higher. In the oceans, the die-off will be even more dramatic. Marine photosynthetic organisms, including phytoplankton that currently produce somewhere between 50 and 85% of Earth's oxygen, will succumb to the same CO2 starvation affecting land plants. Without phytoplankton, ocean food webs will collapse. The oceans, which currently teem with life from the sunlit surface to the lightless depths, will become biologically impoverished, inhabited mainly by anaerobic bacteria clustering around hydrothermal vents and other chemical energy sources. Dead organic matter, no longer oxidized by aerobic decomposers, will pile up in anoxic sediments. Hydrogen sulfide, the rotten egg-smelling gas produced by certain anaerobic bacteria, may accumulate in the oceans and potentially even reach the atmosphere, as happened during several periods of Earth's distant past. This would create a toxic, smelly world utterly hostile to the kind of life we're familiar with, yet life will persist. It always has. Even during Earth's most severe mass extinctions, life found a way. The difference is that after previous mass extinctions, life eventually recovered, diversifying and filling empty ecological niches with new species. Recovery from the oxygen crisis will be impossible because the underlying cause, the brightening sun and depleted CO2, cannot be reversed. Earth is entering a one-way transition toward conditions increasingly hostile to complex life. The rapidity of the oxygen collapse has profound implications for the search for life beyond Earth. Oxygen has long been considered a potential biosignature, a gas whose presence in a planet's atmosphere might indicate the existence of life. But if Earth's oxygen-rich phase lasts only about 2 billion years out of the planet's total 10 billion year lifespan, then oxygen might be a relatively fleeting phenomenon in planetary evolution. Many habitable planets might go through their entire history without ever developing oxygen-rich atmospheres. Astrobiologists may need to search for other biosignatures, gases, or atmospheric features that indicate life without requiring the specific conditions that produce abundant oxygen. For any intelligent beings that might exist on Earth during the oxygen crisis, the situation would be dire. The planet that gave rise to their civilization would be dying around them. They might attempt technological solutions, manufacturing oxygen, growing crops in controlled environments, building enclosed habitats, but these would be temporary measures, buying time rather than solving the underlying problem. Eventually, the resources needed to maintain such systems would run out. The sun isn't going to stop brightening, and CO2 isn't going to magically reappear in the atmosphere. Escape might be the only option. If a civilization existed on Earth 1 billion years from now, it would face a choice: adapt to a low-oxygen anaerobic existence, fundamentally redesigning biological systems in ways that might not be possible, or leave Earth entirely, seeking refuge elsewhere in the solar system or beyond. Mars, ironically, might become more habitable than Earth during this period, as the sun's increased brightness warms the currently frozen Martian surface. The outer solar system, including the moons of Jupiter and Saturn, might offer habitable niches in subsurface oceans warmed by tidal heating and chemical energy. But we're getting ahead of ourselves. The oxygen crisis, catastrophic as it is, represents only the beginning of Earth's transformation. With the biosphere crippled and oxygen levels crashed, the planet enters a new phase of its evolution, one characterized by rising temperatures, evaporating oceans, and the gradual loss of the water that has been such a defining feature of Earth since its earliest days. The world of 1 billion years hence will be hotter, drier, more hostile than anything Earth has experienced in billions of years, and yet, compared to what comes next, this oxygen-depleted world will seem almost benign, because the real heat hasn't even started yet. As we move beyond the oxygen crisis and into the 2nd billion years of Earth's future, the planet enters what scientists call the moist greenhouse phase, a term that understates the dramatic and irreversible changes about to unfold. The sun, now roughly 10% brighter than in our time, pours more energy onto Earth's surface than the planet can efficiently radiate back into space. Surface temperatures are rising year by year, century by century. The few plants that survived the CO2 crash, mostly hardy C4 species eking out an existence in the most favourable locations, continue to decline. The oceans, which have been stable features of Earth for more than 4 billion years, are beginning to change in ominous ways. Water evaporates from the ocean surface into the atmosphere, where it exists as water vapour, a potent greenhouse gas. Normally, this water vapour rises into the atmosphere, cools, condenses into clouds, and falls back to the surface as rain, maintaining a balance. But as surface temperatures climb, more and more water vapour accumulates in the atmosphere before it can condense and return. Water vapour in the atmosphere creates a positive feedback loop. More vapour means more greenhouse warming, which causes more evaporation, which adds more vapour, which causes more warming. This is the moist greenhouse effect, and once it begins, it's extraordinarily difficult to stop. In Earth's current climate system, water vapour cannot accumulate indefinitely in the lower atmosphere because cooler temperatures at altitude cause it to condense into clouds and rain out. But as the surface heats up, the altitude at which condensation occurs rises higher and higher. Eventually water vapour reaches the stratosphere, the layer of atmosphere above the troposphere where weather occurs. The stratosphere is dry, very dry, under normal conditions. Water vapour doesn't belong there. But as the moist greenhouse intensifies, water molecules are transported into the stratosphere in quantities never before seen in Earth's history. And up there, something devastating happens. Solar ultraviolet radiation is intense in the stratosphere, unfiltered by the ozone layer that formed when oxygen was still abundant. This UV radiation breaks apart water molecules, splitting H2O into hydrogen and oxygen atoms through a process called photodissociation. The hydrogen atoms, being extremely light, can escape Earth's gravity entirely, drifting away into space. The oxygen atoms react with other atmospheric constituents or also escape, but either way the water molecule is gone, permanently destroyed. This process, called hydrodynamic escape, has been removing water from Earth's atmosphere since the planet formed, but at such a slow rate that it was easily compensated by volcanic outgassing and the cycling of water through the oceans. Now, with water vapour flooding into the stratosphere, the rate of water loss accelerates dramatically. Earth is bleeding water into space, molecule by molecule, and there's no mechanism to replace it. Models suggest the moist greenhouse phase will fully establish itself somewhere between 1 and 1.5 billion years from now. Once established, it will persist and intensify for hundreds of millions of years, steadily evaporating Earth's oceans. The rate of water loss varies in different models, depending on assumptions about cloud cover, atmospheric circulation, and the efficiency of photodissociation, but most estimates suggest Earth could lose the equivalent of several meters of ocean depth per million years. That might not sound like much, but it adds up. Over 100 million years, that's hundreds of meters of sea level drop. Over 1 billion years, it could be the entire ocean. The total volume of water in Earth's oceans is enormous, about 1.3 billion cubic kilometers, but given enough time and a high enough temperature, even this vast reservoir will evaporate and be lost to space. As the oceans shrink, their remaining water becomes more saline. Salt and other dissolved minerals don't evaporate, so as water is lost, the concentration of these dissolved materials increases. The seas become brine, thick with salt, supporting only the hardiest halophilic microbes. Coastal areas that were underwater are exposed, revealing seafloor sediments baked dry by the intense sun. The continental shelves, once submerged beneath hundreds of meters of water, become dry land, expanding the continents outward. The loss of the oceans has cascading effects beyond the obvious disappearance of marine habitats. Oceans play a crucial role in Earth's climate system, absorbing heat at the equator and transporting it toward the poles through ocean currents. Without this heat distribution, temperature gradients between equator and poles become more extreme. The poles might still be cool enough to retain some ice, while the equatorial regions bake under the relentless sun. Oceans also moderate daily and seasonal temperature variations. Water has a high heat capacity, meaning it takes a lot of energy to change its temperature. Large bodies of water near coastlines keep temperatures relatively stable, preventing extreme swings between day and night or summer and winter. As the oceans shrink and retreat, coastal regions lose this moderating influence. Day-night temperature swings become more dramatic. Seasonal variations intensify. The climate becomes more continental, more extreme. The hydrological cycle, which has distributed fresh water across the continents for billions of years, begins to break down. Rainfall becomes less frequent and more erratic. Rivers dry up as their source glaciers melt and are not replenished. Lakes evaporate, leaving salt flats and dry basins. Groundwater, accumulated over millions of years, is pumped to the surface by geological processes or residual tectonic activity, and then evaporates, not to be replaced. Life, what little remains after the oxygen crisis, retreats to the last refuges, perhaps the poles, where temperatures are still somewhat tolerable, perhaps high-altitude regions where the air is thinner but cooler, perhaps deep underground, where the rock itself provides insulation from the scorching surface. Subsurface aquifers, pockets of water trapped in porous rock layers, might persist for millions of years after the surface has dried completely, hosting microbial communities in darkness. Without liquid water on the surface, plate tectonics becomes unsustainable. Water acts as a lubricant in the mantle, allowing tectonic plates to slide past and beneath each other. As surface water disappears, less water is subducted into the mantle, and the mantle becomes increasingly dry. The rocks become more viscous, more resistant to flow. Tectonic activity slows and eventually ceases entirely. The cessation of plate tectonics has several consequences. Volcanic activity, which depends on the melting of subducted crust, declines sharply. This means less outgassing of CO2 and other gases, further depleting the already thin atmosphere. Mountain building stops, and without tectonic uplift to renew high terrain, the old mountains erode away over millions of years, gradually flattening under the relentless assault of wind and occasional flash floods. The carbon cycle, which has regulated Earth's climate for so long, finally breaks down completely. With no plate tectonics to recycle carbonates and no significant volcanic outgassing to replenish atmospheric CO2, carbon becomes locked in rocks and minerals at the surface. The atmosphere, already depleted of oxygen, loses what little CO2 remains. What's left is primarily nitrogen, along with increasing amounts of water vapour and whatever noble gases and trace constituents haven't escaped to space. Meanwhile, the magnetic field, generated by convection in the liquid outer core, continues to weaken. Estimates suggest the field might collapse entirely somewhere between 2 and 3 billion years from now, as the outer core solidifies due to cooling. Once the field is gone, the solar wind attacks the atmosphere directly. Charged particles from the sun strike atmospheric molecules, imparting enough energy for some of them to escape. The process is slow but relentless, especially for lighter gases. The atmosphere begins to thin. What started as a substantial blanket of gas gradually becomes a tenuous veil. With less atmosphere to distribute heat, temperature differences between day and night become even more extreme. The day side of Earth, facing the sun, heats to extreme temperatures. The night side, radiating heat into the blackness of space with no atmosphere to retain it, becomes bitterly cold. The terminator, the boundary between day and night, might be the only region where temperatures are briefly tolerable, a narrow band migrating around the planet as Earth rotates. Cloud formation, which depends on water vapour, atmospheric pressure, and temperature gradients, becomes increasingly erratic. Some models suggest that as the moist greenhouse intensifies, cloud cover might actually increase initially, as more water evaporates into the atmosphere. Clouds reflect sunlight back into space, potentially providing a temporary break on warming. But this is a transient effect. Eventually, as atmospheric pressure drops and temperatures rise still higher, even clouds become difficult to form and sustain. Through all of this, the sun continues its relentless brightening, adding energy to a system that's already overwhelmed. By the time Earth is 1.5 billion years old, relative to our present day, the sun will be roughly 15% brighter. This doesn't sound like a huge increase, but in terms of actual energy delivered to Earth's surface, it's enormous. The additional heating drives more evaporation, more water lost to space, more atmospheric thinning, more temperature increase, in a vicious cycle that feeds on itself. There's a haunting parallel here to Venus, our sister planet, which underwent a runaway greenhouse effect billions of years ago and transformed from a possibly habitable world with liquid water into the scorching hellscape we observe today. Venus's surface temperature now reaches 460 degrees Celsius, hot enough to melt lead. Its atmosphere, 90 times denser than Earth's, consists almost entirely of carbon dioxide and traps heat so efficiently that the night side is nearly as hot as the day side. Did Venus once have oceans? Did life ever arise there, only to be extinguished when the greenhouse effect spiraled out of control? We don't know for certain, but the possibility haunts planetary scientists. And now Earth seems destined to follow a similar path, not because of anything humans did or could do, but simply because of the Sun's natural evolution. The moist greenhouse phase represents Earth's transition from a living world to a dead one. At the beginning of this phase, around 1 billion years from now, some form of microbial life might still persist in sheltered locations. By the end of it, around 2 billion years from now, even those last holdouts will likely be extinct, unable to survive the heat, the dryness, the intense UV radiation, and the loss of all the complex chemical cycles that life depends on. Earth, a planet that has hosted life for perhaps 4 billion years, will have become sterile. The transformation won't happen overnight, but on geological timescales, it will be swift. And once complete, it will be irreversible. Earth will never again be a living world. The story of life on this planet, which began in the primordial oceans billions of years ago, and culminated in complex ecosystems stretching from the deepest ocean trenches to the highest mountains, will have reached its end. But the planet itself will continue. Rock and metal don't care about temperature or atmospheric composition. Earth will persist, a lifeless sphere of stone, orbiting ever closer to disaster as the Sun continues its inexorable transformation. And the worst is yet to come. 2 billion years from now, give or take a few 100 million years, Earth has become unrecognizable. The oceans are gone, evaporated into space. The atmosphere is a thin, hot envelope of nitrogen and trace gases. The surface temperature hovers between 100 and 150 degrees Celsius, far too hot for liquid water. What little moisture remains is locked in minerals or hidden in deep underground aquifers. Life, if it persists at all, exists only in the most extreme refuges, deep beneath the surface where the rock itself provides insulation from the heat. In this transformed world, two of Earth's most fundamental geological processes are approaching their end: plate tectonics and the magnetic field. Both have been winding down for billions of years, and now, simultaneously, they're about to cease entirely. Plate tectonics has been a defining feature of Earth for at least the last 3 billion years, and possibly much longer. The slow dance of continents, the opening and closing of ocean basins, the rise of mountains and the subduction of seafloor, all of these processes have shaped our planet's surface and made it geologically active in ways that differentiate Earth from every other rocky planet in the solar system. But plate tectonics requires specific conditions to operate. The mantle must be hot enough to flow, creating convection currents that drag the plates across the surface. The lithosphere, the rigid outer shell of crust and upper mantle, must be cool and dense enough to sink back into the mantle at subduction zones. And crucially, there must be water to act as a lubricant, lowering the melting point of rocks and keeping the mantle pliable enough for plates to move. By 2 billion years into Earth's future, all of these conditions are failing. The mantle has been cooling for more than 6 billion years, losing heat to space through the surface. Radioactive decay, which provided much of the internal heat in Earth's early days, has slowed significantly as isotopes with shorter half-lives have decayed away. What remains are long-lived isotopes like uranium-238 and thorium-232, which still produce heat but at a much reduced rate compared to the past. The loss of surface water has been particularly devastating for plate tectonics. Water subducted along with oceanic crust into the mantle has been crucial for maintaining mantle convection and enabling the partial melting that produces magma. Without this water, the mantle becomes stiffer, more resistant to flow. The rocks don't melt as easily. Subduction becomes more difficult. Sometime around this era, plate motion grinds to a halt. The exact timing is uncertain because it depends on factors we can't precisely measure. The initial heat content of Earth's interior, the exact composition of the mantle, the efficiency of heat transport, and the complex feedbacks between all these processes. But whether it happens at 1.5 billion years or 2.5 billion years or somewhere in between, the result is the same. Earth transitions from an active, dynamic world to a static, one-plate planet. What does a world without plate tectonics look like? Mars provides a partial answer. Mars lost its tectonic activity billions of years ago and has been geologically dormant for most of its history. Its surface is ancient, covered in impact craters that have persisted for eons because there's no tectonic recycling to erase them. Volcanoes exist, but they're shield volcanoes over mantle hotspots, not the distributed volcanism associated with plate boundaries. Mountain. Ranges, once formed, erode away over billions of years but are never replaced. Earth after the end of plate tectonics will be similar but worse, because the surface is much hotter. Without tectonic uplift, mountains will erode. Wind, what little of it exists in the thin atmosphere, will sculpt the landscape. Occasional residual volcanic eruptions might occur over mantle hotspots, where particularly hot regions of the deep mantle create plumes that rise toward the surface. But these will become increasingly rare as the mantle cools and solidifies. The carbon cycle, which has already broken down due to the loss of water and the decline in atmospheric CO2, now ceases entirely. Carbonates, the minerals formed when CO2 reacts with rocks, accumulate at the surface with no mechanism to recycle them back into the mantle and release them as CO2 through volcanism. Carbon, the element that was the basis of all life on Earth, becomes permanently locked in the crust, buried and inaccessible. The loss of volcanism also means the end of outgassing, the process by which the interior releases gases to the atmosphere. For billions of years, volcanoes have replenished the atmosphere with water vapour, CO2, sulfur dioxide and other gases. Without this source, the atmosphere becomes even more tenuous. What gases remain are slowly stripped away by the solar wind, by thermal escape, and by chemical reactions with surface minerals. Speaking of the solar wind, its effects become much more pronounced around this same period because Earth's magnetic field finally collapses. The magnetic field, generated by convection currents in the liquid outer core, has been weakening for billions of years as the core slowly cools. The inner core, solid iron and nickel under immense pressure, has been growing as the outer core freezes onto it from the inside out. Convection in the outer core is driven by heat escaping from the inner core, and by compositional differences as lighter elements are excluded when the iron crystallizes. But as the temperature gradient decreases and the amount of liquid iron in the outer core shrinks, the convection becomes weaker and more chaotic. The magnetic field, which results from these convective motions, fluctuates in strength and orientation. Magnetic poles wander. The field might even reverse several times with the north and south magnetic poles swapping positions. Eventually, perhaps around 2 to 3 billion years from now, the outer core becomes too viscous or too thin to maintain convection. The dynamo shuts down. The magnetic field decays over several thousand years, going from a protective shield stretching thousands of kilometers into space to essentially nothing. Without the magnetic field, Earth loses one of its primary defenses against space weather. The solar wind, that constant stream of charged particles flowing out from the sun, now strikes the upper atmosphere directly. These particles collide with atmospheric molecules, sometimes imparting enough energy to knock them free of Earth's gravity entirely. The process is slow, but over millions of years it's devastating. We can see the effects of this process by looking at Mars. Mars lost its global magnetic field about 4 billion years ago, and since then, the solar wind has been steadily eroding its atmosphere. What was once a thicker atmosphere capable of sustaining liquid water on the surface has been reduced to the thin wisp we observe today, with a surface pressure less than 1% of Earth's current atmosphere. Earth's atmosphere, already thinned by the loss of water and the breakdown of the carbon cycle, accelerates its decline once the magnetic field disappears. Nitrogen, the dominant gas, is relatively heavy and doesn't escape easily, but even nitrogen atoms can be lost if they're energized enough by solar wind impacts. Oxygen, already depleted to trace amounts after the biosphere collapsed, continues to decline. Water vapor, what little remains, is broken apart by UV radiation and lost to space. The combination of heat, thin atmosphere, and harsh radiation makes the surface of Earth increasingly inhospitable. Surface temperatures, no longer moderated by a substantial atmosphere, vary wildly between the day side and night side. Where the sun shines, temperatures might exceed 200 degrees Celsius. On the night side, with no atmosphere to retain heat, temperatures could plunge well below freezing. UV radiation, no longer filtered by an ozone layer or scattered by a thick atmosphere, bathes the surface at intensities that would be immediately lethal to any complex organism. Even hardy microbes would struggle to survive such conditions. Any remaining life would need to shelter underground beneath several meters of rock that blocks the UV, or else develop molecular machinery to constantly repair radiation damage faster than it accumulates. In the deep subsurface, conditions might remain tolerable for some forms of life. Radioactive decay in the crust and mantle still produces heat, warming the deep rocks. Pockets of water trapped in the pores and fractures of rock layers might persist for hundreds of millions of years, isolated from the hellish surface. Chemosynthetic bacteria, which derive energy from chemical reactions rather than sunlight, could potentially survive in these deep refuges, living out an existence completely divorced from the surface world. These deep biosphere communities, if they exist, would be Earth's last living inhabitants, the final holdouts of a biosphere that once spanned the entire planet. They would live in eternal darkness, in cramped spaces between rock grains, sustaining themselves on the meagre chemical energy available from reactions between minerals and water. Their populations would be small, their metabolism slow, but they would persist, perhaps for hundreds of millions of years, long after the surface has become completely sterile. The landscape of this future Earth is a vision of desolation. No oceans, no rivers, no glaciers, no forests, no grasslands, no soil. The continents, no longer reshaped by tectonics, erode into gentle rolling plains. Ancient impact craters accumulate, their rims slowly wearing down under the assault of wind and occasional thermal stress fractures. The sky, what little atmosphere remains, might be a strange colour, perhaps a murky brown or orange from suspended dust particles, or maybe a deep purple from the Rayleigh scattering of the sun's light through the thin gases. Dust devils and wind-blown sediment sculpture the landscape into patterns reminiscent of Mars or even Titan, where wind shapes dunes despite an atmosphere only 1.5 times thicker than Earth's will be by this point. The surface is desiccated, thoroughly dried out, with any water locked in hydrated minerals or buried so deep that it's effectively out of reach. And still, the sun continues to brighten. At 2 billion years into Earth's future, the sun is now about 20% more luminous than in our era. The additional energy pours onto Earth's surface, absorbed by rock and dust, converted to heat. The planet glows faintly in infrared, radiating away the excess energy, but not efficiently enough to cool down. This is Earth's new equilibrium, a hot, dry, static world, geologically dead, magnetically silent, atmospherically thin. It bears little resemblance to the vibrant blue planet that gave rise to life billions of years ago. And yet, this is not Earth's final state, not even close. Because the sun hasn't finished its transformation, and the most dramatic changes still lie ahead. 3 billion years from now, Earth is a furnace. The surface temperature has climbed past 200 degrees Celsius, hot enough to sterilize any exposed surface, to oxidize metals, to decompose many minerals. The last water has boiled away centuries ago. The atmosphere, what remains of it, is a superheated vapour, dominated by whatever volcanic outgassing still occurs from residual mantle hotspots, if any remain. The Sun, now roughly 35 to 40% brighter than in our era, floods the inner solar system with energy. Mercury, if it still exists and hasn't been consumed by the gradual expansion of the Sun, is a hellish world with surface temperatures exceeding 400 degrees Celsius. Venus, already an inferno, has only gotten worse. And Earth, once a haven for life, is transitioning into a state that makes Venus look almost benign by comparison. This is the onset of the runaway greenhouse, the final stage before Earth's complete transformation into an uninhabitable rock. The runaway greenhouse is different from the moist greenhouse we discussed earlier. Where the moist greenhouse involved the evaporation of the oceans and the loss of water to space, the runaway greenhouse involves a catastrophic failure of the planet's ability to shed heat. Every planet radiates energy into space in the form of infrared light. The hotter the surface, the more energy it radiates. Under normal conditions, there's a balance. Energy from the sun heats the surface, and the surface radiates heat to space, maintaining a stable temperature. But as the sun brightens and delivers more energy, the surface must get hotter to radiate away that extra heat. There's a problem though. Water vapour and other greenhouse gases in the atmosphere absorb infrared radiation, preventing it from escaping directly to space. This is the greenhouse effect, the same process that keeps Earth warm enough for life under normal conditions, but becomes pathological when pushed to extremes. As the surface heats up, any remaining water evaporates. Water vapour is a powerful greenhouse gas, and it traps more heat. This causes more warming, which causes more evaporation, which traps more heat, in a positive feedback loop. Normally, this would self-limit, because water vapour can only go so high before it condenses and rains out. But if the temperature is high enough, water vapour can flood into the stratosphere, where it's broken apart by UV radiation and lost to space. When we discussed the moist greenhouse, we were talking about a slow process, taking hundreds of millions of years to completely evaporate the oceans. The runaway greenhouse is faster and more catastrophic. It occurs when the amount of infrared radiation the planet can emit to space reaches a fundamental limit, determined by the atmospheric temperature and composition. This limit is called the Komaybayashi-Ingersoll limit, named after the scientists who first calculated it. Beyond this point, adding more energy to the planet doesn't result in more cooling, because the atmosphere is already opaque to infrared radiation. Instead, the extra energy just makes everything hotter. The surface heats up, the atmosphere heats up, and the planet enters a runaway state where temperatures climb without bound until some new equilibrium is reached. For Earth, models suggest this runaway state could be triggered when the solar luminosity reaches about 35 to 40% higher than current values, which corresponds to roughly 3 to 4 billion years from now. Once triggered, surface temperatures could soar to 1,500 degrees Celsius or higher within a relatively short period, geologically speaking. At 1,500 degrees Celsius, rock begins to melt. The surface of Earth, the solid crust that has been stable for billions of years, transitions into a global magma ocean. The continents, those ancient rafts of lighter rock that have survived multiple supercontinent cycles and billions of years of plate tectonics, melt into the sea of molten rock that covers the entire planet. This is a vision of Earth returned to its earlier state, reminiscent of the planet's youth 4.5 billion years ago, when it was entirely molten from the energy of formation and the impact that created the Moon. But unlike that early molten Earth, which cooled and solidified over millions of years to form the crust and eventually support life, this molten future Earth won't cool. The sun keeps pouring in energy, maintaining the magma ocean indefinitely. The atmosphere during this phase would be extraordinary. Water, if any remains, would exist only as a supercritical fluid, neither liquid nor gas, at pressures and temperatures where the distinction becomes meaningless. Other gases released from the melting crust: carbon dioxide from decomposing carbonates, sulfur dioxide from sulfur-bearing minerals, possibly even silicate vapours from the magma itself, would create a thick, choking atmosphere unlike anything Earth has experienced since the Hadean Eon. This atmosphere would be dense, perhaps even denser than Venus's current atmosphere, creating crushing surface pressures. The greenhouse effect would be extreme, with multiple layers of overlapping absorption bands trapping virtually all outgoing infrared radiation. The surface temperature would be determined not by radiative balance, but by the point at which the rock itself can radiate in wavelengths that escape the atmosphere, likely in the far infrared or even at longer wavelengths. Under these conditions, geological processes would be radically different from anything Earth has known. There would be no plate tectonics, obviously, but there might be vigorous convection in the magma ocean, creating currents and upwellings. Differentiation might occur, with heavier minerals sinking and lighter ones rising, gradually sorting the molten crust by density. Over millions of years, this could create a stratified magma ocean, with distinct layers of different compositions. Lightning might be common in this superheated atmosphere, arcing between regions of different electrical potential. Storms, driven by convection and temperature gradients, could rage across the planet, though storm here means something very different from terrestrial storms, more like convective cells in boiling liquid than anything we'd recognise as weather. The night side of Earth, rotating away from the sun, might cool slightly, but not enough to solidify. The atmosphere is so thick and the greenhouse effect so strong that day and night temperatures would be nearly identical, both well above the melting point of rock. Earth has become a tidally locked world in terms of temperature distribution, even though it still rotates. Seen from space, Earth would glow dull red, like a coal in a furnace. The thick atmosphere might be opaque to visible light, hiding the molten surface beneath, but infrared observations would show the intense heat radiating from the planet. Any observer looking at Earth from a distant vantage point would see a world transformed beyond recognition, a planet that has transitioned from life-bearing to life-destroying to completely alien. Could anything survive this? Almost certainly not. The temperatures are far too high. Water, the essential solvent for life as we know it, cannot exist in liquid form. The UV radiation from the now much brighter sun would be intense enough to break apart complex organic molecules. Any complex chemistry beyond simple gas phase reactions would be impossible in such an environment. Even the deep subsurface, the last refuge we speculated about earlier, would be uninhabitable. The heat from the surface would penetrate downward, warming the entire crust. Kilometres deep rocks that were cool enough to potentially harbour life would be heated beyond the survival limits of even the most thermophilic extremophiles. Earth would be sterile in the most complete sense, devoid of life not just at the surface but throughout its entire volume. This state might persist for hundreds of millions of years, or even longer, depending on how the sun continues to evolve. But Earth's story isn't over yet. In fact, the most dramatic chapter is still to come, because the sun, having grown steadily brighter for billions of years, is about to undergo a transformation that will dwarf everything we've discussed so far. The sun is running out of hydrogen fuel, and when that happens, when the nuclear furnace at its heart sputters and begins to die, the sun will enter its red giant phase, swelling to enormous size and releasing energy that will make its current output seem trivial by comparison. Earth, already a molten hellscape, is about to face its ultimate trial: survival in the atmosphere of a red giant star. 5 billion years from now, the sun has a problem. For more than 9 billion years, it has been fusing hydrogen into helium in its core, converting mass into energy through nuclear fusion. This process produces an outward pressure that balances the inward pull of gravity, keeping the Sun stable. But hydrogen, abundant as it is finite, and the Sun has been burning through its supply at a rate of about 600 million tons per second for its entire main sequence lifetime. Now, the hydrogen in the core is nearly exhausted. What remains is helium, the ash of fusion, which has been accumulating at the centre of the Sun for billions of years. Helium doesn't fuse easily. It requires much higher temperatures and pressures than hydrogen fusion, temperatures that the core hasn't yet reached. So fusion in the core begins to slow and then stops. When fusion stops, the outward pressure drops. Gravity, which has been held in check for 9 billion years, asserts itself. The helium core begins to collapse under its own weight, growing smaller and denser. As it contracts, gravitational potential energy is converted to heat, and the core temperature rises. This seems counterintuitive. The Sun is running out of fuel, so it should cool down, right? But stellar physics doesn't work that way. The core collapse releases enormous amounts of energy, heating the core to temperatures higher than it ever reached during the main sequence phase. Meanwhile, the hydrogen surrounding the inert helium core is now hot enough and under enough pressure to begin fusing. A shell of hydrogen fusion ignites around the core, producing energy at a prodigious rate. This shell-burning phase produces more energy than the core ever did, and that energy has to go somewhere. It pushes outward on the overlying layers of the Sun, causing them to expand. The Sun begins to grow. Its radius increases slowly at first, then more rapidly. The outer layers of the Sun, pushed outward by the energy from the hydrogen-burning shell, become cooler as they expand, transitioning from yellow-white to orange-red. The Sun is becoming a red giant. This transformation doesn't happen instantly. It takes millions of years for the Sun to make the transition from main sequence star to full red giant. But on cosmic timescales, it's rapid. Around 5 to 5.5 billion years from now, the Sun will exit the main sequence. Over the next billion years or so, it will swell to many times its current size. How big will it get? This is a crucial question for Earth's fate, and the answer is uncertain. Current models suggest the Sun might expand to somewhere between 100 and 256 times its current radius. At the upper end of these estimates, the Sun's surface would extend past the current orbit of Mars. Even at the lower estimates, it would engulf Mercury and Venus with certainty and would come perilously close to Earth's orbit. The fate of Mercury is sealed. This small, dense world, orbiting just 58 million kilometers from the Sun, will be consumed when the Sun expands. The red giant's tenuous outer atmosphere will envelop Mercury, and atmospheric drag will cause its orbit to decay. Within perhaps a few hundred years after first contact with the Sun's atmosphere, Mercury will spiral inward and be destroyed, vaporized in the blazing heat of the Sun's deeper layers. Venus suffers the same fate shortly thereafter. Although Venus orbits farther from the Sun than Mercury, at about 108 million kilometers, it's still well within the maximum expansion radius of the red giant Sun. The thick Venusian atmosphere, which made Venus so hellish for billions of years, offers no protection against being enveloped by a star. Venus will spiral into the Sun and be destroyed. But what about Earth? Earth currently orbits at 1 astronomical unit, about 150 million kilometers from the Sun. Whether this is far enough to escape the expanding Sun is one of the great uncertainties in predicting our planet's ultimate fate. The answer depends on 3 factors: exactly how large the Sun grows, how much mass the Sun loses during the red giant phase, and how tidal interactions affect Earth's orbit during this period. Let's consider each in turn. The maximum size of the red giant Sun is uncertain, because it depends on complex modelling of the Sun's internal structure, the efficiency of energy, transport from the core to the surface, and the rate of mass loss from the outer layers. Different models give different answers, with maximum radii ranging from about 0.85 astronomical units to as much as 1.5 astronomical units. If the Sun expands to the lower end of this range, Earth might just barely escape being engulfed. The Sun's surface would come close, within perhaps 20 million kilometres, but wouldn't quite reach Earth. If the Sun expands to the upper end of the range, Earth would be well within the Sun's atmosphere, doomed to spiral inward and be destroyed. The mass loss issue is equally important. During its red giant phase, the Sun will experience an intense stellar wind, losing mass at a much higher rate than today. Current models suggest the Sun might lose 25 to 30% of its total mass over the course of the red giant phase, which lasts several 100 million years. When a star loses mass, the gravitational pull on its planets weakens and orbits expand. This is described by Kepler's laws of orbital mechanics. If the Sun loses enough mass, Earth's orbit could expand outward, potentially enough to escape the expanding Sun, even if it would otherwise have been engulfed. The rate of orbital expansion depends on how quickly the Sun loses mass. If the mass loss is gradual, orbits expand smoothly. But the Sun's evolution isn't perfectly smooth. There will be periods of rapid mass loss, possibly associated with thermal pulses or other instabilities in the star's interior. During these events, the Sun might briefly brighten by many times its normal luminosity or eject large amounts of material in a short period. Tidal interactions complicate the picture further. As the Sun expands and becomes a red giant, its outer layers will be very diffuse, like a tenuous atmosphere. If Earth passes through these outer layers, even briefly, it will experience atmospheric drag. This drag will slow Earth's orbital motion, causing its orbit to decay. The planet will spiral inward, closer to the Sun. Whether tidal drag or orbital expansion dominates depends on the details of the Sun's structure and mass loss rate. Different researchers have reached different conclusions. Some studies suggest Earth will be consumed by the Sun shortly after Mercury and Venus. Other studies suggest Earth's orbit will expand faster than the Sun grows, allowing our planet to escape, albeit barely. One detailed study by Klaus-Peter Schroeder and Robert Smith, published in 2008, modelled the Sun's evolution with particular attention to mass loss and tidal effects. They concluded that Earth will not survive. According to their model, when the Sun is about 7.59 billion years old, about 3 billion years older than today, it will reach maximum size and will extend to about 1.2 astronomical units. By that time, Earth, despite some orbital expansion due to mass loss, will have spiraled inward due to tidal drag to about 0.98 astronomical units. The Sun will engulf Earth. The end, when it comes, will be swift. Earth, a dead molten rock having survived billions of years of increasing solar radiation, will find itself skimming through the outer atmosphere of a red giant star. The drag will slow its orbital speed. The orbit will decay, not over billions of years, but over mere thousands of years, a cosmic eye blink. Earth will spiral inward, getting closer and closer to the Sun's core. The temperatures will be unimaginable. The molten surface, already at 1,500 degrees from the runaway greenhouse, will heat further. The rock will transition from molten to vaporized. Earth's atmosphere, thick with silicate vapor and other rock-forming elements, will be stripped away by the intense radiation and stellar wind. The planet's mass will begin to diminish as material is ablated from the surface. Deeper into the Sun's atmosphere, the temperature and pressure continue to rise. Earth's solid core, iron and nickel under tremendous pressure, might survive a bit longer than the rest of the planet, but eventually even this will succumb. The iron will vaporize. The atoms will be ionized by the intense radiation, stripped of electrons to form a plasma. What was once a planet becomes a cloud of ions, mingling with the Sun's outer atmosphere, adding a tiny amount of heavier elements to the star's composition. Spectroscopic observations of a red giant star that recently consumed a planet might show unusual abundances of elements like iron, nickel and silicon in its spectrum, the only memorial to a world that once existed. If Earth somehow survives, if the most optimistic mass loss scenarios are correct, and our planet's orbit expands enough to avoid engulfment, its fate is only slightly less grim. The red giant sun, even at a safe distance, will be thousands of times more luminous than the sun we know today. Earth's surface will be heated to thousands of degrees. Any remaining crust will be completely molten. The planet will be a sphere of liquid rock, glowing brightly in infrared light, tidally locked or nearly so to the bloated sun, with one hemisphere permanently baking under the intense radiation, and the other side slightly cooler but still well above melting temperature. In either scenario, whether consumed or merely scorched, Earth as any recognizable entity will have ceased to exist. The planet's 4.5 billion year history as a geological body, with continents and oceans and life, will have ended. The atoms that once made up the mountains and oceans, the soil and the trees, the dinosaurs and the trilobites, and every living thing that ever existed will be scattered, incorporated into the sun, or orbiting as a molten remnant. But the sun's story isn't over even here. After reaching its maximum size as a red giant, after consuming or nearly consuming the inner planets, after shining with the brilliance of 1,000 present-day suns, the sun will enter the final chapters of its own stellar life, and in doing so, it will reshape what remains of the solar system one last time. After several 100 million years as a red giant, having swollen to enormous size and shed a substantial fraction of its mass into space, the sun faces its own mortality. The helium core, which has been contracting and heating throughout the red giant phase, finally reaches a temperature of about 100 million Kelvin. At this temperature, helium fusion can ignite. The process is called the triple alpha process because it involves 3 helium nuclei, alpha particles, fusing together to form carbon. This reaction produces energy, reigniting nuclear fusion in the core and temporarily halting the core's collapse. The sun stabilizes for a time, fusing helium into carbon and oxygen in its core while continuing to burn hydrogen in a shell around the core. This helium-burning phase is brief, lasting perhaps only 100 to 200 million years. Helium fusion produces less energy per unit mass than hydrogen fusion, and the sun's helium supply is much smaller than its original hydrogen supply. The helium runs out quickly. When the helium is exhausted, the sun faces a final crisis. It doesn't have enough mass to ignite carbon fusion, which requires even higher temperatures than helium fusion. Only stars with more than about 8 times the sun's mass can fuse carbon and continue up the periodic table until they build iron cores and explode as supernovae. The sun's mass, reduced by the loss of material during the red giant phase, is well below this threshold. Without a new fusion reaction to provide energy, the core begins to collapse again. But this time, the collapse is halted not by ignition of a new fuel, but by quantum mechanical effects. The electrons in the core, squeezed into an incredibly small volume, reach a state called electron degeneracy. The Pauli exclusion principle, a fundamental rule of quantum mechanics, states that no 2 electrons can occupy the same quantum state. When electrons are packed tightly enough, this principle creates an outward pressure that resists further compression. The core stabilizes as a degenerate electron gas, a state of matter utterly unlike anything we experience in everyday life. The core is incredibly dense, roughly 1 million times denser than water, which means a sugar cube-sized chunk of this material would weigh as much as a car. Yet it's also incredibly small, roughly the size of Earth despite containing about half of the sun's original mass. This dense, inert core is the remnant of what was once a star, a white dwarf. But the outer layers of the sun, still surrounding the contracting core, don't collapse quietly. The core's contraction releases energy, heating the surrounding layers and driving them outward. Over the course of several tens of thousands of years, the sun will eject its outer layers in a series of pulses, creating an expanding shell of gas moving outward into space. This expanding shell, illuminated by ultraviolet radiation from the hot core, glows brightly in colourful emission lines, creating what astronomers call a planetary nebula. The term is misleading. Planetary nebulae have nothing to do with planets. They're called that because in small telescopes, their round shapes reminded early astronomers of planets. But they're actually the death shrouds of stars, the final shedding of a dying star's atmosphere. The Sun's planetary nebula will expand at perhaps 20 to 30 kilometers per second, which sounds fast but is leisurely by cosmic standards. It will take tens of thousands of years for the nebula to reach the orbit of Neptune, where it will begin to interact with the outer solar system. By then, the nebula will have faded, its gases dispersed and diluted until they're nearly invisible. What remains at the centre of this expanding nebula is the white dwarf, all that's left of the Sun. This stellar remnant is about the size of Earth, but contains roughly half the Sun's mass, giving it a surface gravity about 100,000 times stronger than Earth's. An object dropped onto a white dwarf would accelerate to tremendous speed and hit the surface with an impact that would vaporize it. The white dwarf is initially very hot, with a surface temperature exceeding 100,000 Kelvin, which makes it appear bluish-white, hence the name white dwarf. But it has no internal source of energy, no fusion, no gravitational contraction, nothing to produce heat. The white dwarf is simply cooling off, radiating away its stored thermal energy into space. The cooling process is extremely slow. White dwarfs are excellent insulators because their degenerate matter conducts heat poorly. They cool at a rate determined by how fast photons can leak out from the interior to the surface and escape into space. This cooling takes trillions of years, far longer than the current age of the universe. 8 billion years from now, around the time the Sun becomes a white dwarf, the solar system will be transformed beyond recognition. Mercury and Venus are gone, consumed during the red giant phase. Earth, if it survived, is either a scorched remnant in a wider orbit or it too was destroyed. Mars might have survived, pushed to a more distant orbit by the Sun's mass loss, but it's a cold, dead world, frozen solid with no internal heat and no atmosphere. The outer planets, Jupiter, Saturn, Uranus, Neptune, have also been pushed outward by the Sun's mass loss. Their orbits are now 50 to 100% larger than they were when the Sun was on the main sequence. These giant planets will survive the Sun's red giant phase intact. They were far enough away that the expanding Sun never reached them, and they're massive enough that the stellar wind and radiation, while intense, couldn't strip away their atmospheres. However, these planets will have changed. The intense radiation during the red giant phase, when the Sun was thousands of times more luminous, would have heated their atmospheres and caused some atmospheric loss, particularly for Uranus and Neptune, which are less massive than Jupiter and Saturn. The moons of these planets, which have been frozen ice worlds for billions of years, would have experienced a brief period of warmth, possibly melting surface ice and creating temporary oceans. This raises an intriguing possibility. Could life arise on these moons during the red giant phase? When the Sun swells to red giant size, its habitable zone, the region where liquid water can exist on a planetary surface, moves outward dramatically. For a time, perhaps a few 100 million years, the moons of Saturn or Jupiter might be in this zone. Europa, Enceladus, Titan. These moons, which we speculate might have subsurface oceans today, could have liquid water on their surfaces during this brief warm period. Could life emerge in such a short time? On Earth, life appeared very quickly once conditions were suitable, possibly within a few 100 million years of the planet's formation. If these moons already harbour subsurface biospheres, as some scientists speculate, then the warming could allow this life to flourish on the surface, at least temporarily. It's a tantalising scenario, life rising in the outer solar system just as the Sun is dying. But this warm period is brief. Once the Sun becomes a white dwarf, its luminosity drops precipitously. The white dwarf Sun, despite its high surface temperature, is so small that it emits far less total light than the main sequence Sun. Models suggest the white dwarf will have only about 0.1% of the Sun's current luminosity initially, dimming further as it cools. The solar system plunges into darkness and cold. Any life that emerged on the moons during the red giant phase will freeze, unless it can retreat back underground to subsurface oceans warmed by tidal heating. The planets, now orbiting a dim white dwarf instead of a bright star, become frozen worlds lit only by the faint glow of the stellar remnant. For the giant planets, this isn't too different from their current state. Jupiter and Saturn are already so far from the Sun that solar radiation contributes little to their energy budget. They're actually warmer than you'd expect from sunlight alone because they still have internal heat left over from their formation. This internal heat will sustain them for billions of years, gradually diminishing as they radiate energy into space. If Earth survived as a scorched rock in orbit around the white dwarf, it will cool and solidify. The molten surface, maintained at high temperature by the red giant sun's radiation, will radiate its heat into space. Over millions of years, the surface will cool enough to solidify, forming a crust once more. This crust will be unlike anything Earth has known before, a perfectly smooth sphere with no plate tectonics to create mountains or valleys, no water to erode features, just a slowly cooling ball of solidified rock. The white dwarf sun will continue to cool and dim over trillions of years. Its colour will shift from bluish-white to yellow to red as its surface temperature drops. Eventually, after many trillions of years, far longer than the current age of the universe, it will cool to the point where it no longer emits visible light at all. At that point it's called a black dwarf, a dark cinder of degenerate matter, the ultimate endpoint of stellar evolution for stars like the Sun. No black dwarfs exist yet in the universe, because the universe isn't old enough for any white dwarf to have cooled that much. The oldest white dwarfs, formed from stars that died shortly after the first galaxies formed, are still radiating heat. They'll continue to do so for trillions of years to come. The white dwarf solar system will be a quiet place. No stellar wind to speak of, no solar flares, no radiation storms, just the planets and their moons, orbiting in silence around the fading ember of what was once a vibrant star. Occasionally a comet from the Oort cloud might fall inward, its orbit perturbed by a passing star, and pass close to the white dwarf, where the intense gravity would tear it apart and create a ring of debris. In fact, astronomers have observed exactly this phenomenon around some white dwarfs. Debris disks and pollution of the white dwarf's atmosphere, with elements like calcium, magnesium, and iron that must have come from disintegrated rocky bodies. These observations tell us that planetary systems, or at least their remnants, do survive the death of their stars and continue to exist around white dwarfs. And so the solar system will persist, orbiting the white dwarf remnant of the Sun, for time scales that dwarf even the billions of years we've been discussing. The planets will continue their orbits for trillions upon trillions of years, slowly spiralling outward as the white dwarf loses mass to an incredibly faint stellar wind, or spiralling inward as gravitational radiation slowly drains energy from their orbits. But in the vastness of time ahead, even these stable orbits will eventually change in ways we need to explore next. 10 billion years from now, the Sun is a white dwarf, slowly cooling, emitting only a faint glow. The planets that survived the red giant phase continue their orbits, but the solar system is no longer isolated. It orbits within the Milky Way galaxy, which is itself undergoing dramatic changes. And over the timescales we're now discussing, hundreds of billions to trillions of years, the environment in which the solar system exists will fundamentally transform. The first major event happens relatively soon, astronomically speaking. The Milky Way galaxy and our neighbour, the Andromeda galaxy, are currently approaching each other at about 110 kilometres per second. This collision has been inevitable for billions of years, and around 4 to 5 billion years from now, roughly the same era when the Sun becomes a red giant, the two galaxies will begin to merge. Galaxy collisions sound violent, but they're actually quite gentle on the scale of individual stars. Galaxies are mostly empty space. The stars are so far apart that even when two galaxies merge, direct stellar collisions are extraordinarily rare. What does happen is that the gravitational interactions between the two galaxies dramatically reshape both of them. The merger will take several billion years to complete. The two galaxies will pass through each other, their mutual gravity distorting the neat spiral structures into chaotic streams and tidal tails of stars. They'll separate, slow down, and fall back together, passing through each other again. Over the course of multiple passages and billions of years, they'll gradually settle into a single merged galaxy, likely an elliptical galaxy rather than a spiral. This new galaxy, sometimes informally called Milkomeda, will be larger than either the Milky Way or Andromeda, containing perhaps 1 trillion stars. The Sun, assuming it still exists as a white dwarf by then, will be flung into a new orbit within this merged galaxy. Its position relative to the galactic centre will change, and its orbital period around the centre will be different. The night sky, if anyone were around to observe it, would be spectacular during the merger. Andromeda, currently visible as a faint smudge in the night sky from Earth, would grow larger and brighter over millions of years, eventually dominating the sky. During the actual passages, the sky would be filled with swirling streams of stars, nebulae, and the bright cores of both galaxies. But from the perspective of any surviving planets, the merger is fairly uneventful. The Sun's own planetary system, the tiny bubble of space gravitationally bound to the Sun, is so small compared to the scale of the galaxy that it remains intact during the merger. The planets continue their orbits, unaffected by the cosmic reshuffling happening around them. However, the merger does increase the probability of close encounters with other stars. In the dense star fields created during the merger, particularly in the core of the new elliptical galaxy, stars pass relatively close to each other more frequently. Close here is still measured in fractions of a light year, not close enough for stellar collisions, but close enough for gravitational perturbations. When another star passes within a light year or so of the Sun, its gravity tugs on the outer planets and comets. Comets in the Oort cloud, that distant reservoir of icy bodies surrounding the solar system, can be perturbed into new orbits. Some might be ejected from the solar system entirely. Others might be sent plunging inward toward the inner solar system. The outer planets themselves might have their orbits altered slightly. If a passing star comes particularly close, within perhaps 1/10 of a light year, it could even eject one of the outer planets from the solar system entirely, sending it wandering through interstellar space as a rogue planet. These close encounters will become increasingly common as time goes on. The Sun orbits within the merged galaxy, and over billions of years it will pass through different regions with varying stellar densities. Sometimes it will be in relatively sparse regions where encounters are rare. Other times, particularly if it passes through the dense galactic core, encounters could happen every few million years. Eventually, billions of years after the galaxy merger, the solar system will likely lose most or all of its planets to close encounters with other stars. Current estimates suggest that over timescales of about 1 quadrillion years, 10 to the 15th power, or 1,000 trillion years, gravitational interactions will eject most planets from their star systems. Where do these ejected planets go? They become rogue planets, wandering through interstellar space, no longer bound to any star. These lonely worlds drift through the galaxy, gradually cooling. If Earth somehow survived as an ejected planet, it would be a cold, dark world, lit only by the faint glow of distant stars and whatever internal heat remains in its core. Interestingly, some of these rogue planets might eventually be captured by other stars. If a rogue planet happens to pass close to another star system at just the right speed and angle, it could be gravitationally captured and enter orbit around the new star. Models suggest this process could create a second generation of planetary systems around white dwarfs and other stellar remnants. The white dwarf sun itself will also be affected by these encounters. Over even longer timescales, perhaps 100 quadrillion years, stellar close encounters will gradually alter the white dwarf's orbit around the galactic centre. Sometimes these encounters will add energy to the orbit, pushing the white dwarf farther from the galactic centre. Other times they'll remove energy, pulling it closer. Most stars in a galaxy will eventually be ejected into intergalactic space through these cumulative gravitational interactions. About 90 to 99% of all stars will be flung out of their galaxies over these immense timescales. The white dwarf sun could share this fate, ejected from the merged Milky galaxy to wander in the vast emptiness between galaxies. The remaining stars, those that aren't ejected, will gradually spiral inward toward the galactic centre due to dynamical friction and other gravitational effects. Eventually, over timescales of perhaps 10 to the 19th power years, 10 million trillion years, these remaining stars will encounter the supermassive black hole at the galaxy's centre and either be torn apart by tidal forces or consumed whole. The white dwarf sun has about a 10 to 20% chance of eventually falling into the galactic centre's black hole. If this happens, the white dwarf will be destroyed, its degenerate matter torn apart and added to the black hole's mass. This would be the sun's ultimate fate, consumed not by its own death throes, as its inner planets were, but by the maw of a black hole billions of years after it ceased being a star. But let's consider the more likely scenario, where the sun is ejected from the galaxy. Wandering through intergalactic space, the white dwarf would be truly alone, separated from other stars by millions of light years. Any remaining planets or asteroid debris would continue to orbit, but the sky would be almost completely dark, devoid of the bright stars and nebulae visible from within a galaxy. Over truly vast timescales, even these orbiting planets face an unusual fate. Einstein's general theory of relativity predicts that orbiting bodies emit gravitational waves, ripples in the fabric of space-time that carry away energy. For normal orbital systems, this energy loss is utterly negligible. Earth orbits the Sun, emitting gravitational waves, but the amount of energy lost is so tiny that it would take far longer than the current age of the universe for the orbit to decay noticeably. But we're now discussing timescales far beyond the current age of the universe. Over periods measured in 10 to the 20 power years, 100 quintillion years, or more, even this tiny energy loss becomes significant. Slowly, imperceptibly, the orbits of any remaining planets around the white dwarf sun will decay. The planets will spiral inward, getting closer and closer to the white dwarf, until eventually they fall into it. When a planet collides with a white dwarf, the white dwarf's intense gravity tears the planet apart and spreads its material into a disk around the stellar remnant. This disk gradually accretes onto the white dwarf, adding its mass to the star. If enough material accumulates, interesting things can happen. But for individual planets like Earth, the collision is simply the final endpoint, the last chapter in a history that began 4.5 billion years ago with the formation of the solar system. By the time these processes have run their course, the universe will be unimaginably old and almost unimaginably empty. The stars that illuminated the cosmos for tens of billions of years will have exhausted their fuel and faded away. New star formation, which has been declining for billions of years as galaxies run out of the gas needed to form stars, will have ceased entirely. The universe will enter a new era, one dominated not by bright stars and bustling galaxies, but by darkness, cold, and the slow decay of matter itself. To fully appreciate Earth's fate, we need to zoom out beyond the solar system and consider the broader evolution of the universe. Our planet's story is intimately tied to the Sun, yes, but the Sun itself exists within a galaxy, and the galaxy exists within a universe that is itself evolving and changing on timescales that dwarf even the life of stars. The universe as we know it began roughly 13.8 billion years ago in the Big Bang. In the first few 100 million years, the first stars formed, massive and short-lived, enriching the cosmos with the heavier elements forged in their cores and scattered when they exploded as supernovae. These elements seeded the next generation of stars, including the Sun, which formed about 9 billion years after the Big Bang. We currently live in what cosmologists call the stelliferous era, the age of stars. This era, which began a few 100 million years after the Big Bang, is characterized by the formation and evolution of stars. Stars dominate the visible universe, producing light and heat, creating the conditions for planets and life. But the stelliferous era won't last forever. Star formation requires raw materials, gas, primarily hydrogen and helium, that can collapse under gravity to form new stars. Galaxies contain vast reservoirs of this gas, but it's being steadily consumed. Every time a new star forms, it locks up some of this gas. Over time, as more stars form and the gas supply dwindles, the rate of star formation declines. Current observations show that star formation in the universe peaked about 10 to 11 billion years ago and has been declining ever since. The decline is slow but inexorable. In our own galaxy, the rate of star formation has dropped significantly from its peak, and most of the stars being born now are low-mass red dwarfs, which require less material than larger stars. This trend will continue. In about 1 trillion years from now, give or take a few 100 billion years, the last stars will form in the universe. After that, no new stars will be born. The stelliferous era will end, not with a bang but with a whimper, as the final wisps of gas collapse into the final generation of stars. What kinds of stars will these be? Almost certainly low-mass red dwarfs, which can form from the smallest amounts of gas and which burn their hydrogen fuel so slowly that they can shine for trillions of years. The smallest red dwarfs, with masses around 8 to 10% of the Sun's mass, have theoretical lifespans exceeding 10 trillion years. These tiny stars will be the universe's last beacons of light, shining dimly but persistently long after the Sun and all other Sun-like stars have burned out. They'll illuminate a universe that has grown vast and empty through cosmic expansion. Other galaxies, which we can see in the sky today, will have receded beyond the cosmic horizon, carried away by the expansion of space to distances so great that their light can never reach us. This process has already begun. The universe is expanding and the expansion is accelerating, driven by dark energy, a mysterious component of the cosmos that acts as a kind of anti-gravity. As the universe expands, galaxies that aren't bound together by gravity drift apart. The local group of galaxies, which includes the Milky Way, Andromeda, and about 50 smaller galaxies, will remain bound together and eventually merge into a single large galaxy. But everything beyond this local group is moving away from us. Within about 100 billion years, all galaxies outside the local group will have receded so far that their light can no longer reach us. Any astronomers existing in this distant future, observing from within the merged Milky galaxy, would see a universe containing only their own galaxy, surrounded by darkness. They would have no way to observe other galaxies, no way to detect the cosmic microwave background radiation, no way to determine that the universe is expanding. They would likely conclude they live in a static, eternal universe consisting of a single galaxy. This has profound implications for cosmology. Many of the key discoveries we've made about the universe, the Big Bang, the expansion of space, the existence of dark matter and dark energy, rely on observations of distant galaxies and the cosmic microwave background. In the far future, these observations will be impossible. Future civilizations, if any exist, will be cosmologically blind, unable to determine the true nature and history of the universe. Meanwhile, the stars continue to die. The Sun becomes a white dwarf around 8 billion years from now. More massive stars die sooner, some as supernova, leaving behind neutron stars or black holes. Less massive stars die later, becoming white dwarfs themselves. By about 120 trillion years from now, all the stars in the universe will have exhausted their fuel. What remains is a universe full of stellar remnants, white dwarfs, neutron stars, and black holes, along with brown dwarfs, failed stars that never quite accumulated enough mass to ignite hydrogen fusion, and planets, both those still orbiting dead stars and rogue planets wandering through intergalactic space. This is the beginning of the degenerate era, the age after stars have died. The universe is dark now, lit only by the occasional flash when two brown dwarfs collide and briefly fuse their hydrogen, or when a white dwarf accretes enough material to undergo a nova or supernova explosion. These events become increasingly rare as time goes on. Even the white dwarfs are cooling. After 1 quadrillion years or so, white dwarfs will have cooled to the point where they emit virtually no light at all, becoming black dwarfs. The universe will be truly dark, with no natural sources of light except for the faint glow of accretion disks around black holes and the occasional supernova. But matter itself may not be stable on these timescales. Some theories in particle physics predict that protons, the building blocks of atomic nuclei, might not be stable forever. If protons decay, then over timescales of 10 to the 34th power years or more, all the matter in the universe, planets, white dwarfs, brown dwarfs, everything, will gradually disintegrate into lighter particles. This would be the dark era, when even black holes are gone, evaporated away by Hawking radiation, over timescales of 10 to the 100 power years for the largest supermassive black holes. What would remain is a universe filled with photons, neutrinos and electrons, all diluted by the expansion of space until the density becomes vanishingly small. This ultimate heat death of the universe, predicted by thermodynamics, represents the final state: maximum entropy, uniform temperature, no gradients of any kind, no structure, no change, no events. Just a cold, dark, infinitely expanding void. But we're getting far ahead of ourselves. These timescales are so vast they're almost meaningless. For perspective, the current age of the universe is less than 14 billion years. 10 trillion years is more than 700 times the current age of the universe. 10 to the 100 power years is... well, there aren't enough atoms in the observable universe to write out that number in full. For our purposes, tracing Earth's fate, we don't need to go quite that far. Earth's story effectively ends when it's either consumed by the Sun during the red giant phase, around 7 to 8 billion years from now, or when it's ejected from the solar system by a stellar encounter, potentially within the next trillion years. After that, Earth is either gone or a cold, dead rock wandering through space, no longer recognizable as the world we know. But before we conclude our journey, let's take one final look at the ultimate endpoints, the final chapters in the story of matter and energy in the cosmos, just to appreciate the full scope of cosmic time and the ultimate fate that awaits not just Earth, but everything that exists. We've traced Earth's story from our present day through the oxygen crisis, the evaporation of the oceans, the runaway greenhouse, the red giant sun, and the white dwarf era. We've seen our planet transition from a vibrant living world to a dead rock and finally, perhaps, to complete destruction. But what about the universe itself? What happens to everything in the immense gulfs of time that stretch beyond even the death of stars? The answer depends on assumptions about physics at energy scales and timescales far beyond anything we can test in laboratories. But our best theories make some intriguing predictions. After the last stars burn out, about 120 trillion years from now, the universe enters the degenerate era. This era is dominated by stellar remnants, white dwarfs, neutron stars, and black holes. These objects will be the primary massive objects in the universe for timescales that dwarf the entire previous history of the cosmos. Over the next quadrillions and quintillions of years, these remnants undergo slow but inexorable changes. Gravitational interactions between stars and stellar remnants gradually alter their orbits within galaxies. Most will be ejected into intergalactic space, as we discussed earlier. The few that remain will eventually fall into the central supermassive black hole at their galaxy's core. Meanwhile, the stellar remnants themselves are evolving. White dwarfs cool down, becoming black dwarfs, dead lumps of degenerate carbon and oxygen that emit no light. Neutron stars also cool, though they remain hot for much longer than white dwarfs due to their smaller surface area. Occasionally, two white dwarfs orbiting each other will spiral inward due to gravitational wave emission and merge. If their combined mass exceeds about 1.4 times the Sun's mass, the Chandrasekhar limit, the merged white dwarf will collapse and explode as a Type Ia supernova. These explosions, bright enough to outshine an entire galaxy for a few weeks, will be among the few sources of light in this dark future universe. Such collisions will become increasingly rare as white dwarfs drift apart due to the expansion of space and are ejected from galaxies by gravitational interactions. But they'll continue to happen, occasionally, for immense periods of time. Models suggest supernovae from white dwarf collisions might continue to occur, somewhere in the universe, until perhaps 10 to the 21st power years from now. Black holes represent a special category of stellar remnant. Unlike white dwarfs, which eventually cool and become inert, black holes can theoretically evaporate through a quantum mechanical process called Hawking radiation. Stephen Hawking showed that black holes aren't perfectly black. They emit a faint thermal radiation due to quantum effects near their event horizons. For stellar mass black holes, those formed from supernova explosions, Hawking radiation is utterly negligible. These black holes are so massive and their temperature so low that they emit virtually no radiation. But they are emitting something, and over vast timescales, this radiation adds up. A stellar mass black hole 10 times the mass of the Sun would take about 10 to the 67th power years to evaporate completely. Supermassive black holes, like the one at the centre of our galaxy with millions or billions of solar masses, take even longer. The largest supermassive black holes might not evaporate until 10 to the 100 power years from now. When a black hole finally evaporates, it does so in a spectacular way. As the black hole loses mass, its temperature increases, smaller black holes are hotter, and the rate of evaporation accelerates. In its final moments, the black hole would explode in a burst of radiation and particles, the last flash of light from an object that once swallowed everything that fell into it. But even before black holes evaporate, matter itself might decay. The proton, one of the building blocks of atomic nuclei, is extraordinarily stable. As far as we know, protons live essentially forever. But some theories in particle physics, particularly grand unified theories that attempt to explain all the fundamental forces as different aspects of a single force, predict that protons should eventually decay into lighter particles. If protons decay, the timescale is extraordinarily long, at least 10 to the 34th power years. Experiments have placed lower limits on the proton lifetime at around 10 to the 34th power years, meaning if they decay at all, it must take at least that long. If protons do decay, then over periods measured in 10 to the 35th power to 10 to the 40 power years, all the matter in the universe would gradually disintegrate. White dwarfs, made of degenerate electrons and atomic nuclei, would slowly decay as their constituent protons disappeared. The white dwarf would become less massive, emitting a faint glow from the energy released by proton decay. Eventually it would evaporate entirely, leaving behind only electrons and the decay products of protons. Neutron stars and planets would suffer the same fate. Everything made of ordinary matter, atoms, molecules, rocks, metals, everything, would gradually decay into radiation and leptons. The universe would be left with photons, neutrinos, electrons and positrons, all diluted to incredibly low densities by the expansion of space. If protons don't decay, the timeline is different but the endpoint similar. Over timescales of 10 to the 65 power years or longer, quantum tunneling could cause matter to reorganize itself. Solid objects would gradually flow and reshape as atoms randomly tunnel from one location to another. Over immense periods, even large objects like planets or white dwarfs would become spherical and smooth through this quantum diffusion. Eventually, around 10 to 100 power years, the exact timescale depends on assumptions about quantum mechanics, even the most stable arrangements of matter could theoretically tunnel into black holes. An object like a white dwarf, given enough time, could undergo quantum tunneling into a more compressed state, forming a black hole. This black hole would then evaporate through Hawking radiation. In either scenario, proton decay or quantum tunneling into black holes, the ultimate state of the universe is similar. After all black holes have evaporated, after all matter has decayed or tunneled away, what remains is a sea of photons and leptons, spread ever thinner by the relentless expansion of space. The temperature of the universe approaches absolute zero. The density approaches zero. The expansion continues forever, driven by dark energy, creating more and more space between the scattered particles. Eventually, the average distance between particles becomes so vast that most particles are causally disconnected from each other. The distance is so great that not even light will ever be able to travel from one particle to another before the yacht's expansion carries them hopelessly far apart. This is heat death, the ultimate fate predicted by thermodynamics, a state of maximum entropy where no gradients exist, no energy flows, no events occur, no structure persists. The universe becomes an infinitely expanding, infinitely cold, infinitely diffuse sea of radiation and isolated particles, eternally unchanging because there's nothing left to change. Could anything interesting happen in such a universe? Some speculation suggests that quantum fluctuations might eventually, over timescales of 10 to 10 to the 56 power years or even longer, spontaneously create new universes through quantum tunneling. A small region of space might fluctuate into a higher energy state and inflate into a new Big Bang, creating a new universe within the dead expanding husk of the old one. These timescales are so vast they lose all meaning. To put it in perspective, if the current age of the universe were compressed into a single second, 10 to the 100 power years would be longer than 10 to the 90 power seconds, which is far longer than the number of Planck times that have elapsed since the Big Bang. We're talking about timescales that dwarf anything comprehensible. And yet, this is what physics predicts, based on our current understanding of thermodynamics, quantum mechanics, and general relativity. The universe will continue, probably forever, expanding and cooling and becoming ever more diffuse, until nothing remains but the faintest whisper of radiation in an infinite void. For Earth, for the Sun, for every planet and star and galaxy, the story ends long before this ultimate heat death. Our planet's fate is sealed within the next 8 billion years, consumed by the Sun or left as a dead remnant. The Sun itself fades to a black dwarf within trillions of years. The solar system disperses, the galaxy merges and eventually evaporates its stars, and all the structures we can observe today, stars, galaxies, clusters, dissolve into the expanding darkness. But for now, here in our brief moment of cosmic time, Earth remains a vibrant living world. The timescales we've discussed are so immense that they're almost irrelevant to our existence. 8 billion years from now, humanity will either be long extinct or transformed beyond recognition. The very concept of Earth as a specific planet with a specific history will have been forgotten and rediscovered countless times. And yet, understanding this timeline gives us perspective, a sense of our place in the vast sweep of cosmic history. We've travelled through more than 7 billion years of Earth's future, watching as our familiar blue planet transforms into something utterly alien and ultimately meets its end. We've witnessed the slow death of photosynthesis, the evaporation of the oceans, the collapse of the magnetic field, the runaway greenhouse effect, and finally, the consumption of Earth by a red giant sun, or its survival as a scorched remnant orbiting a cooling white dwarf. The timeline we've explored is sobering. Earth, as a habitable world capable of supporting complex life, has perhaps only 1 to 2 billion years remaining. That sounds like a vast amount of time, and by human standards it is. Civilization has existed for perhaps 10,000 years. Written history spans a mere 5,000 years. 1 billion years is 100,000 times longer than all of recorded human history, and yet, compared to how long Earth has been habitable, it's relatively brief. Life has existed on Earth for roughly 4 billion years. Complex multicellular life has existed for at least 600 million years. If Earth's history as a living world were a day, we're in the late afternoon, with only a few hours left before sunset. This realization shifts our perspective. We often think of Earth as eternal, unchanging on timescales beyond human concern. But the story we've traced shows that Earth's hospitality to life is temporary, a phase in the planet's evolution bounded by the past formation of the oceans and atmosphere and the future brightening of the sun. Does this mean Earth's fate is tragic? In a sense, yes. All that has lived, all the magnificent diversity of life that has evolved over 4 billion years, will eventually be extinguished by forces beyond anyone's control. The sun will keep brightening because that's what stars do. The oceans will evaporate because water vapour is a greenhouse gas. The carbon cycle will break down because plate tectonics requires water and a cooling interior. These are inevitable consequences of physics and chemistry. But there's also something beautiful in this inevitability. Earth's story is part of a larger cosmic narrative, the evolution of stars and planets, the transformation of matter and energy across the eons. The atoms that make up your body were forged in stars that died billions of years ago. They've cycled through planets and asteroids, through the solar nebula that formed our solar system, through countless living organisms on Earth, and eventually they'll be scattered again, perhaps consumed by the sun, perhaps ejected into interstellar space, perhaps becoming part of some future world orbiting some future star. Nothing is permanent. Everything changes. Stars are born, shine for a time and die. Planets form, evolve, and are destroyed. Galaxies merge and disperse. Even the universe itself has a beginning and will have an end, or at least a transformation into a state so different from what we know that it might as well be an end. This impermanence applies to us as well. Humanity, or whatever we evolve into or are succeeded by, will not witness most of the events we've described. Long before the oceans boil away, long before Earth becomes uninhabitable, our species will either be extinct or transformed beyond recognition. If our descendants do survive into the far future, they'll likely have left Earth, spreading to other worlds, adapting to new environments, perhaps even engineering themselves to thrive in conditions we'd find utterly hostile. The far future belongs to whoever and whatever can survive and adapt. Perhaps life will spread from Earth to other worlds before our planet becomes uninhabitable, carrying forward the story that began in the primordial oceans 4 billion years ago. Perhaps one day, billions of years from now, beings descended from Earth life will watch from a distant solar system as our sun swells into a red giant and consumes the world where their ancestors first evolved. Or perhaps not. Perhaps life is rare, and Earth's biosphere is a unique occurrence in this corner of the galaxy. Perhaps life will arise elsewhere, on other worlds orbiting other stars, beginning the cycle anew. The universe is vast and old, and there's time for countless stories to unfold. What we can say with certainty is that Earth, this particular rocky planet orbiting this particular star, will not last forever. Its time as a living world is finite, bounded by the evolution of the sun, and that makes every moment of Earth's habitability precious. We live in a golden age, a brief window of cosmic time when Earth is perfectly suited to support complex life. The temperature is just right. Liquid water covers most of the surface. The atmosphere is breathable. The magnetic field protects us from radiation. Plate tectonics cycles nutrients and regulates the climate. All of these conditions are temporary, and all of them will eventually fail, but for now, they persist. For now, Earth remains our home, the only place in the universe where we know for certain that life exists, and that knowledge should inspire both humility and action. Humility, because we're part of a story much larger and longer than ourselves, players in a cosmic drama that began billions of years ago and will continue for billions more, and action, because the time we have is precious and limited, not just on geological timescales, but on human timescales as well. The challenges we face today, climate change, biodiversity loss, resource depletion, operate on timescales of years to centuries, not billions of years. They're urgent in ways that Earth's eventual fate is not. But understanding the deep future gives us perspective. It reminds us that Earth is both resilient and fragile. Resilient because the planet has survived countless catastrophes over its 4.5 billion year history. Fragile because the conditions that make it habitable are the result of a delicate balance of factors, many of which we're now perturbing. We cannot prevent the sun from brightening. We cannot stop plate tectonics from eventually ceasing. We cannot reverse the long-term evolution of our planet and star. These are cosmic inevitabilities, written into the laws of physics. But we can right now, in this brief moment we have, take care of the world that has nurtured us and every living thing we've ever known. So as we close this exploration of Earth's far future, let's return to the present. Look around you. Feel the air you breathe, the water you drink, the solid ground beneath your feet. All of these are temporary gifts, products of billions of years of cosmic and geological evolution. Earth won't be habitable forever, but it's habitable now, and that makes all the difference.